On this adventure, we're going to introduce the direct product and look at several examples of the direct product. Alright, here we're going to define a new group. Given two groups G and H, the new group is going to be on their Cartesian product, where the Cartesian product is a set of ordered pairs, where the first coordinate has to be an element in the first set, and the second coordinate has to be an element in the second set. So this is a set of all ordered pairs of that form. Our product is going to be called pointwise multiplication. Given us two ordered pairs, the product is an ordered pair whose first coordinate is the product of the first coordinates, and whose second coordinate is the product of the second coordinates. In fact, this is what it would have to be because the first coordinates live in one group, and the second coordinates live in what might be a different group. So for all G and G prime, and all H and H prime. And something we'll prove in a later video is G times H is a group. In fact, you've already seen this in an earlier course before, because in earlier courses, the most common group is R under addition. And you look at R times R, and they usually call this R squared. And so the group operation's addition, and you're looking at pointwise addition. This is vector addition, which is often described with this whole drawing and the parallelogram law. So the parallelogram law is a special case of this operation. And we won't discuss it much in this course, but you can also iterate the direct product. And so R to the n is a generalization of this operation. So given multiple groups, G1 through Gn, you can do the same thing. You're looking at sequences and same type of operation. So that's one example. Let's look at examples of finite groups, though. Let's look at Z mod 2Z times Z times 3Z. So Z mod 2Z has two elements, 0 bar and 1 bar. So the first coordinate has two values, either 0 bar or 1 bar. While the second coordinate has three possible values, 0 bar, 1 bar, and 2 bar. It is worth pointing out here that this 1 bar in the first coordinate is supposed to represent the odd numbers, the set of all odd numbers, while the 1 bar in the second coordinate is actually all numbers of the form 3q plus 1. So they're not the same thing, even though we're using the same notation to denote both of them. They're elements in different groups, so even though we're using the same symbol, they're not actually the same thing. Alright, so there's our rows. There's 6 possible ordered pairs because there's 2 possible first coordinates and 3 possible second coordinates. Here they all are. The identity element in the first coordinate, identity element in the second. So when I do addition here, I'm going to get everything back because 0 plus anything, any first coordinate is going to give me that other first coordinate. And second coordinate 0, 0 plus whatever second coordinate I get is going to give me that second coordinate. So I'm going to get the first row back exactly like I should. Alright then, now let's add this 0, 1 bar to everything. Well, the first coordinate is 0, that's the identity element here. So I can just copy the first coordinates just fine. 1 bar changes the second coordinate by 1. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, which is 0 mod 3. and then the second coordinates repeat. So the second coordinates here are just copies. Now here I'm adding the second coordinate by 2. So 0 plus 2 is 2, 1 plus 2 is 0 mod 3, 2 plus 2 is 1 mod 3, and repeat. Good news, since the second coordinates repeat this pattern here, 0, 1 bar, 2 bar, all the second coordinates up here repeat themselves. 0, 1 bar, 2 bar, 0, 1 bar, 2 bar. And so that allows me to write down the second coordinates quickly in the bottom half of the table, because I'm just doing the same calculations again. 0 plus 0, 0 plus 1, 0 plus 2, 0 plus 0, so on and so forth. Keep that in mind if you ever have to fill out a Cayley table for a product of groups. That if you structure the table correctly, you'll see that you're only having to do the calculations once. So I only really need to focus on what the first coordinates are. So 0 plus 1 is 1 bar. And 1 plus 1 is 2, which mod 2 is 0. And so now I've finished my Cayley table. Now let's look at properties of it. It is symmetric, so this is an abelian group. Even something more interesting happens if I look at 1, 1. Well, 1 plus 1 is 2, 2. That's 0, 2. Plus 1 again is 1, 3. Well, that's 1, 0. Plus 1 again is 0, 1. Plus 1 again is 1, 2. Back to 0, 0. So if I just take one of the generators from each of the products, and I look at the group cyclic subgroup generated by that generator, I actually get the whole group, because I got all 6 elements. So this group is actually cyclic, which means it's isomorphic to Z mod 6Z, which is pretty amazing. Of course, one might think that something like that might be true in general, but there's a nice counterexample, Z2 mod Z2. It's known as the Klein 4 group. You can check that if you try the same trick, you're going to get 0, 0, 1, 1, but 1 plus 1 is 0, 0 again. You're only going to get 2 elements, but the group has size 4. And you can check that if you take the other 2 non-zero elements, you're also going to get cyclic subgroups of size 2. So it's not cyclic. This is the symmetry group of the rectangle, actually, if you check it out, because every element is order exactly 2. And the product of any 2 of them is the third. 0 plus 1, 0, 1 plus 1, 0 is 1, 1, and so on. So it turns out we start to get evidence for the following theorem that we need to prove, that the direct product of 2 cyclic groups is isomorphic to a cyclic group on the product of the 2 numbers, if and only if the 2 numbers are relatively prime. We will prove that eventually using an interesting approach. The textbook also proves it directly, so you can take the textbook's approach as well, but the textbook also goes into internal direct products, and I find that as an interesting, I like to apply that theory to this example.